All right, everyone, we are back and we are going to do our Pset 3 solution videos. So, studying dissolved oxygen content of pond by the gym, a population mean, so that means that our mu equals 86, our population standard deviation, sig, is equal to 16, and we're asked to solve for our confidence intervals here. So, with this information, we can take our PDF and our normal distribution, our Gaussian distribution, and we can go ahead and we can solve for this, knowing that the z function, we're trying to solve for our x's for a mu of 86 and a sig of 16. So let's go ahead and solve. So what we want to do is we want to integrate the PDF function from a value of, and let's just call this we'll integrate the function, the PDF from z, from a value of this z function. It's actually going to go to x. Actually, let's go to minus x. Let's see if we can do it as such. I'm trying to solve this in a little bit of a slick way. And we want the integral of this to be 0.36. So our 36% confidence interval. Let's do numerically. It doesn't seem to like this. But what we can do is we take a z function and a minus z function. Yeah, that's the problem. So what we'll do is go like this. Minus x to plus x, or just x. So this is our x value. It's not really the x, it's actually our z value. So then we can go and solve. So for z function of x, and then 86, and then 16, solve when this equals this value here. And we can solve for that. So this gives us our first confidence interval value. This would give us our next value. And there we go. So we can do the same thing here, and we'll just change the value. So that would be 0.36. How about a 10% confidence interval? So we should see even a kind of a sharper, like a lower range of values. So if we do minus z, whoops, it'd be 83. And if we look at that and compare, you see it's much sharper around essentially our mean. And the same thing here. Good. What about 90? Whoops. 1.64. We can solve for that here. This minus value. What about 95? 1.96. Plug it in. Minus. How about plus? Yep. And then 99. And then we can go from here. There. Wider and wider because we're containing more of our data set. Excellent. So we got it. Now let's go to problem 2. What percent of the data will exhibit a concentration greater than 70? So now what we're going to do is we're going to integrate the PDF from a z value, and we want greater than 70. So 70 is our lower bound. So we're going to do z function of our x value, which is 70. Mean is 86. This is 16. So z function here to infinity, because it's all greater than this. And again, you can double check these values and do it kind of the handwritten way, or you can just use it with our function here. There we go. And this should make sense because if we think about it, right, we have, and it's always really good to draw like we've done in class, this is 86, this is 70. So just to give a rough check, our value has to be greater than 0.5 because we're always looking at everything greater than 70, which must be at least 0.5. So that's at least a good rough check. But we've done this before in class quite a bit. How about less than 72? So now we're going to go to minus infinity to 72. And then we're going to delete this infinity here. And that should also be, so 72 we see again is on this side. Less than, it should be less than 0.5. And that's indeed the case. How about greater than 90? So we're going to just go to the same thing here. This should be less than 0.5. So let's go ahead and do 90. And we see, yes, indeed. Oh, actually, that's 80. See? Good double check so I don't make a typo. That should be less than 0.5, and it indeed is. What percent will be between 90 and 102? All we have to do is integrate between here and here. 90 and 102. That will also still be less than, it will definitely still be less than 0.5. And unfortunately, I've clipped the help button, and now it's going to wait. Actually, here we go. 90 and 102. Yep, and then 90 between 102. How about 68 and 112? We'll just change it here. 68, 112, and 0.817. Fantastic. If I make 978 measurements, how many concentration measurements will be greater than 65? So let's go from 65 to infinity. This is our percentage, but now if we have number of measurements, I need to multiply by the number of measurements n, which is 978. And I'm just going to do this numerically. And then I'll get my number of measurements. Greater than 65, how about less than 92? So let's do less than 92, so times 978 from minus infinity to 92. This should be greater than half. Yep, and indeed it is. Less than 92, how about greater than 115? This should be also less than half. Or not also, but less than half. Good. If a sample exhibits a concentration of 120, is that an outlier? So remember, we said an outlier is going to be when we have some measure in x that is equal to mu plus or minus 3 sigma. So if we're outside those bounds. So if we're taking our mu, 86 plus 3 times 16, or 86 minus 3 times 16, that is going to be our bounds. So, is 120 an outlier? No. What about 50? Nope. They're both not outliers. And then finally, we're looking at our 4 data files that are attached here. 90% confidence intervals. And are any statistically significant? What distribution do these look like? Well, let's go into R. We're going to set our working directory here, not here, because this is from an old one. So I'm going to go set my working directory. And I'm going to copy this because I'm going to use this for future YouTube videos and solutions. So I'm going to Control Enter, Enter, set my working directory. I'm going to read in. Ooh, I think there's a typo here. Oops, not there. I think there's a typo. Oof. That's another typo. So I don't have a D4. I think that's just 3. So I need to make another typo. Only D1 to D3. So now let's go ahead. Where's my RStudio? And I'll just double check to make sure that is indeed the case. And it looks like it is indeed. So let's go ahead. So I'm going to read each of these in. D1, D2, D3. Let's just take a look at them just to see what the data looks like. And here we see D1, D2, D3. So I'm going to pull out the second column because that's what I'm concerned about. I want to look at Control Enter here. So this is my 90% confidence interval. Here it is here. And then here it is here. Remember, they're statistically significant if they overlap. So we can actually look at those values. So let's look at, so for 1, it's 0.957 and 1.01. So that is not going to overlap with 2 at all, but it will overlap. Or does it overlap here? Yes, it is. It is going to overlap. 1 and 3 are not statistically significant, but 2 is statistically significant from 1 and 3. You could also look at that using, and actually we can look at the distributions here. here, and here. So we can actually see these values plotted as such here. So you can see that those look all pretty. If we go back through that again, 1, 2, they're pretty normally distributed. This one looks a little bit funky, but you can change the, let's do 20 bins maybe. That might make it worse, but yeah, it looks pretty normally distributed for the most part. Excellent. In the future, we're going to learn how to do basically box plots. So actually, we can look at, actually, let's take, for example, let's create, it's hard to show them one at a time, and especially putting them all together. We have to do data.frame. So we could actually just look at it, but you could eventually combine that data set. Yeah, actually, we can combine that data set, and then we can look at essentially the box plots and combine those all together. But we can see that those are overlapping, so there's multiple ways to look at this. So that's pretty much it. So actually, I can do it real quick. But we've already proved that here. You can do that pretty easily in Mathematica as well. But we'll save that for another. Actually, yeah, I'm interested. So D1, D2, D3, I'm going to pull these out. Look at this. So actually, I'm going to do this here. My list equals this. D1, D2, D3, fantastic. Import list 1. Let's look at It's taking a little bit. Great. So I'm going to take all of the second column, all the rows, second column. I'm going to go from 2 to -1 in terms of the rows. So now I'm going to do table, and then I'm going to go from I, loop over that I from 1 to length. Length, list, LENGTH of list. Boop, boop. Good. So now we're going to do box whisker chart of our data set. And then what we're going to do on the box whisker because it's showing outliers. Box whisker chart. We can give it some, basically, we want to look at some, I don't want to look at outliers. I don't want to look at the, I want to look at the notches. So we're going to go, oops, pull this here. Notched. Because that gives us our confidence interval here. Because this is giving max and min and, the 75th quartile, 25th quartile, all that stuff. But we just want to look at, I'm actually going to pull this up a little bit larger. So we want to look at basically these notches, which should give us our 95% confidence interval. So we can see if we can actually, set our confidence intervals here. Let's see. Chart element function. Method scaling, frames, ticks. This is kind of the hard part about some of these automatic functions. And I just kind of played around here because I wanted to see. Notched. See, this is also the median. It's not giving me my 95% the confidence intervals. Yeah. So that's why, again, graphically it's nice to look at this, but unless you're doing this, you'd have to basically look at and specify those the confidence intervals here. It's possible to do, but it's going to be a little bit tough. So instead, calculate it yourself. You can do it there. You can also do, for example, mean CI, and you can get those confidence intervals as well. You have to import another package in Mathematica, but that's pretty much it. So that's your solution for problem set 3. Fantastic. See you next time. Bye.